So today we will discuss this flow control function of data link layer. Yesterday we were discussing two other functions. One is framing. So we saw character oriented framing and bit oriented framing, and in both cases we saw this byte stuffing and bit stuffing. So those who were not able to attend yesterday's class, please check the the recorded classes. I don't see anyone looking into this recorded classes, so I am very doubtful whether I need to upload it, but there is no extra effort involved in this process other than just uploading it, because I am recording it straight away. Anyway, we'll start it. So then we saw the physical addressing as another function of the data link layer, physical addressing. So you refer to the physical address as the link address or the MAC address. Did someone try these things? Someone try this ifconfig command or ipconfig command? Anyone? Give a try on that. Please do, because if you have access to a PC or a laptop or anything, so just give this commands a try, because down the line we may have assignments. So those who don't have access to a PC or laptop, please do tell me personally that time, when I say about an assignment will be an online assignment. It won't involve much of writing or anything. Rather, you will need to send me screenshots of things, running commands. Okay, so this is two other important roles of data link layer are flow control and error control. So flow control is also dealt in the transport layer of the TCP/IP model, but TCP/IP protocol suite. But at primitive way, it is also done at the data link layer. Now remember, this data link layer is sandwiched between the network layer and the physical layer. So this means that so at the physical layer you have bits, and at the network layer you have packets. So data link layer should provide a service, is providing a service to the network layer, and it makes the network layer comfortable. It makes the physical layer may have lot of errors, loss of bits, bits might get corrupted in the channel, all those things. Your data link layer should make it appear to the network layer that there are no problems there. So some problems that are there in the physical layer, like some bits are corrupted, or so that all those things have to be dealt in the data link layer, and it has to pass an error-free service, give an error-free service to the network layer. That is the role of the data link layer. That is why we have this error detection and correction as a function. Error detection, error control. So both you have to detect errors, and some cases you have error correction also. If you have, you may take up some paper called as cryptography or information security. There you will study about forward error correction and all such algorithms, all such things. So these two functions are called as data link control, flow control and error control. So why do we need flow control? That is a simple, we'll just illustrate with a simple example. Say you have a sender which is keep on sending packets, keep on sending frames at some particular rate. Now the receiver may not be ready always. We'll assume in a ideal situation where the receiver is always ready, and it's sending receiving those frames, and it is putting it in a buffer. Now there is not a case where you have you can buffer infinite number of frames. So because there is a limit to buffering infinite number of frames, so there may be chance of some frames getting lost, then so that means you have data loss. So, or you have another alternative to solve this issue is that you can have a buffer with finite capacity. Buffer is always with a finite capacity, where you can buffer some frames, then provide some feedback to the sender that, see, my buffer is full, I am not ready. So that way you will be able to control the flow of frames from the sender to the receiver. So such feedback mechanism is required. So that is done using flow control. And datalink layer, different datalink layer protocols have different strategies for flow control. So we will see some strategies in this, and we'll elaborate more on the flow control as well as flow control strategy in the when we discuss transport layer. The transmission control protocol or TCP has a very efficient mechanism to deal with flow control. So say this is the analogy. I'll tell you, am I fast? Can I move? Can I carry on this class at this speed, at this pace? Same way the sender can ask. Or the receiver can provide a feedback, say it's okay or whatever. So this is the flow control strategy. So there are 4 protocols. Traditionally these are described as simple protocol, that is without any flow control. Then there is a stop and wait flow control, and these two, the last two, go back and selective repeat, these are together classified as sometimes they are together classified as sliding window protocols. Sliding window protocol. So we'll deal with the first two today. We'll deal with the first 2 protocol. So flow control, as already mentioned, this happens at the transport layer. So symbol protocol. Symbol protocol. Is the class with me? Yes, the class is with me. Only 26 people are there. So a simple strategy of flow control is a simple protocol. Say there is no flow control or error control, nothing. The receiver will just receive the frames and the sender is just sending the frames. And it's an ideal situation. There is no way to control it. So you can describe this operation of a protocol, a data link protocol, by means of something called as a finite state machines. You might have learned this in the digital electronics, logic system design. Finite state diagram, state machines.
Yes, sir.
Same thing. Same way, you have a initial state, and when some event occurs, there is a transition to another state. So we'll describe only 2 states. So we'll describe only 2 states for this simple protocol. You have say a state where it is ready and it is just sending the frame. This is the sender side and this is the receiver side. These are 2 FSMs. This is mentioned. So this is the data link layer, and you have a packet coming from the network layer. So its task is to make a frame and just send it. So when the packet comes, that is an event. Then it will just send it. Packet comes, send. The frame arrived, deliver the packet. Frame arrived means that is a event. So it will be delivering to the network layer. That is the simple aspect. So that is a simple strategy and simple protocol. Now there are this is something called as a flow diagram. In your papers, you will be asked, it is always better to draw these diagrams, because by now you will be aware that this data communication paper is more or less a descriptive paper. You need to memorize a lot of things. So and the examiner is not going to scan through the entire thing. Rather, he or she will be looking for diagrams and all those things. So have this diagram in your mind. This is a simple diagram which shows why this is slanted, because there is some delay. These lines are, there is this axis is say there is a trip delay. That's why it's slanted. It's shown slanted. Otherwise, it would have drawn straight. So this is the sending node. So node is sending a packet to the data link layer. Data link layer makes a frame and sends it to the receiving. Then again it gets a packet, makes a frame, sends it. There is no feedback or nothing provided by the receiver to the sender. It's a very ideal situation. It's not a practical case. In a practical case, frames may be lost. The receiver might have problems. It might be short of buffers, its data link layer might be slow, its processor might be slow, it might have a backlog. All those things are there. So to have much more a better way of dealing with this, you have as a stop and wait protocol. Don't ever make slides for seminar like this. Okay, don't ever make slides for seminar like this, because this is a very bad way of making the slides. Just to illustrate this point, I made this slide. It's always better to have small bullets and elaborate the things. Just because I'm going to give the slides to you, I just put the things in a compact way, typed out the things in a compact way. Other than that, never make slides like this. Okay. So that is why you don't, I mentioned a point in that handout, don't have block text in the in the slides. So this has both flow control as well as error control, and what the option is that the transmitter will send a frame and then it will turn on a timer. Why? That we'll see later. So a transmitter will send a frame and it will wait for an acknowledgement. So after sending this frame, it will turn on a timer. So timer will say, I'll wait for 5 minutes for an acknowledgement, something like that. And if the acknowledgement doesn't come within 5 minutes, I'll assume that the frame is lost. Frame may be lost, the data frame may be lost, or even the acknowledgement can be lost. Either of these things can happen. Either of these things can happen. So that is the situation here. So in addition to this, there are something which is to detect errors. Stop and wait protocol has something called as a CRC bit. So CRC bit, how we'll discuss how the CRC bits are generated in the next part after the flow control, after we discuss flow control. But for the present, you assume that there are some bits which are transmitted, which are generated using specific polynomials. 8-bit CRC, 16-bit CRC, 32-bit CRC codes are there. These are added to the frame. So you have the frame plus some CRC bits, cyclic redundancy code, that is what CRC. So this bits are sent and this is half duplex line. At a given time, this half duplex, they can't communicate simultaneously. This is a half duplex communication, the stop and wait protocol. So it is sending data frame with a CRC bit. At the receiver data link layer, the CRC bit is checked, and if the CRC bit is correct, you will do the reverse algorithm, that is reverse computation, check computation as that done in the sender side, and then if you get a correct thing, the CRC bit turns out to be correct, then the data frame is packed, means the packet is sent to the network layer of the receiver. Else what happens? Else it is assumed that the packet is damaged. So that is what is mentioned here. At the correct means the frame is good, and CRC bit is incorrect means the frame is corrupted, and it will just discard that frame. So discard the frame means it won't be sending out an acknowledgement. So acknowledgement is there, I have got a frame. So acknowledgement is sent if the frame is a valid, correct, uncorrupted frame. It will be sending an acknowledgement frame, and the acknowledgement frame will should arrive at the sender before the timer expires. So if it arrives at 5 minutes and 1 second, it's late, it's closed. The sender will assume that the frame is lost, the data frame is lost, and it will again retransmit. So again retransmit means, to retransmit it again means the before sending, the sender will have to keep a copy of this frame that is sent, so that in the event that the frame is not correctly received, or the acknowledgement is lost, there should be a scope for retransmission. The data is available for retransmission. So it will wait, that is why stop and wait. So it will send a frame, wait for an acknowledgement, that is stop and wait. And if the acknowledgement doesn't arrive within this, before the timer times out, it will retransmit the frame. Now this so this is not an efficient way of doing this thing, and it is a half duplex way, but still some protocols do use this strategy. So so that is if the CRC is correct and the acknowledgement frame is received at the receiver before the timer expires, the timer is stopped and the transmitter will send the next frame. So I'll use these terms interchangeably, sender and transmitter. Okay, don't get mixed up, that's why I included it here. Now if the CRC is incorrect, is assume that the receiver data link layer assumes that the frame is corrupted, and it will just discard the frame. Now the timer waits for, say, for instance, 5 minutes. It's not 5 minutes, I just gave a duration like that. 5 minutes is a very long time. It's in a few milliseconds, you can say. So the timer expires, and the timer will assume that either the frame is lost or a frame is corrupted. That means the CRC bit is having error, or even the acknowledgement frame is lost. So in either case, the timer has to retransmit the frame. Okay, so this is the nutshell of the stop and wait protocol. You will see this thing as a finite state machine. So this is the sender side and the receiver side. Any doubts about the previous slide we discussed about stop and wait? Shall we move on to the what is a finite state machine? Yes, no? Classes with me? Let me see, people are there, 27 people are there, someone joined midway. So I assume that you don't have any doubts. So the sender side, you have two states, one is a ready state and a blocking state. The sender can transition between either of these two states, and the receiver side, there is only one state. It is ready to receive a frame and check the thing, all those things. Okay, so we'll check the sender side. Sender side, the process that begins this thing is that a packet is coming from the network layer. You will make a frame, keep a copy in the buffer and send the frame. And before sending the as soon as the frame is sent, you will turn on a timer. Now turn on the timer means you will have two options. Say you will wait for an acknowledgement. You are waiting for an acknowledgement. So acknowledgement means so acknowledgement has to come. So you are we'll just see the situation here. So when the error free frame comes here, so it will extract this data and deliver it to deliver the packet to the network layer and send the acknowledgement. So acknowledgement is received. So acknowledgement is received at the this is when the timer is turned on, it is waiting for an acknowledgement. It will stop the timer and it will discard the saved frame. You have already saved a copy. So it is now ready to send the next frame. Now in the event that you are having a CRC bit error in the frame which is arriving there, you will discard the frame. So the timer will time out and it will restart the timer and send that copy. Okay, now again there is another probability that the acknowledgement is corrupted. You will discard the acknowledgement and you will again retransmit. Duplicate frames. There is a situation for duplicate frames. That is what the duplication of frames can happen, because here in this case we'll see this thing in the diagram, say on this flow diagram. This is the ideal case where you are transmitting a frame and you are obtaining it at this layer, error free frame, and acknowledgement is sent back, and it is say before the timer times out, the acknowledgement reaches the sender and it will say send the next frame 2, I can say. So second frame is lost. So timer times out, again it is sending that thing. It is resending that frame, so it gets back an acknowledgement. That's fine. Again, that's fine. So the third packet is made as a frame. It is getting to the data link layer of the receiver. Acknowledgement is generated. Acknowledgement is lost. Acknowledgement lost even though the frame is received intact. So the channel does not distinguish between a data frame or an acknowledgement frame while introducing errors. It's for it everything is bits, and noise can come at random. So the frame is corrupted means it will assume that the frame, due to some reason, the frame is not received here. It will again resend the frame. So what happens? You will duplicate this frame twice. So the same frame is duplicated. So this has to be somehow prevented. So there is a possibility of preventing this thing to some extent by giving sequence numbers to the frames and the acknowledgements. So sequence numbers to the frames and acknowledgements. You will put the sequence numbers as a simple way as 0 and 1. So so this is a way to do this thing using sequence numbers. Your transport control, the transport layer, the transmission control protocol does these things in a much more efficient way. There are when we come to that, you will gain a good working understanding of how this thing process happens. But as of now, just understand this. You are sending the frame, you are numbering the frame as 0, 1, 0, 1, alternate 0 and 1. Acknowledgements are numbered with 1, 0 like that. It's alternating. So you are sending a frame 0 and you are getting an acknowledgement 1. So the sequence number in the acknowledgement indicates the next frame which the receiving node expects. So this is under the assumption that there is enough of data to be sent, okay, from the sender side. Okay, so it sends, the sender sends, transmitter sends a frame 0, it delivers, receives an acknowledgement with a sequence number 1. So again it understands that I can send the next frame. So that is a frame with the frame number 1. It sends, it's lost. Lost means it is again resent. Resent, it's retransmitted. Retransmitted. So and it is received correctly. Everything is fine. The data link layer of the receiver sends an acknowledgement frame with a sequence number 0, indicating that it expects the new frame with a sequence number 0. So the transmitter sends a frame with a sequence number 0, makes a frame from a data packet from the network layer, sends a sequence puts a sequence number 0 and sends. The acknowledgement is sent back as ACK1, but the acknowledgement frame is lost. So what happens? The frame 0 is again retransmitted after the timeout duration. When the timer times out, it will retransmit this frame, the same frame which has been buffered. When it gets here, the data link layer here understands that I was expecting a frame with the sequence number 1, but I got that is why it is indicating that ACK1. I was expecting a frame with the sequence number 1, but I got a frame with the sequence number 0. What happens? It will just discard this frame. So you can prevent duplication. Now there are various funny questions that could be asked. What happens in the case where the sequence number itself can get corrupted? Yeah, that's also a possibility. But we consider it cannot be considered as a very rare event even. But there in that case you have CRC bits to indicate that there is an error. What happens if the CRC bit itself is corrupted? So it's based on probability. The entire communication theory is based on probability. So you have a probability based on the various factors. So you will say it's like conditional probability. So so that is depending on this. So in this situation you are discarding this duplicate frame 0 and it again transmits ACK1 so that the sender can send a frame, correct data frame with a sequence number 1. So this is preventing duplication. So next day we shall discuss the remaining protocols, that is the sliding window protocol, as well as sliding window protocol. You have go back in and selective repeat. There is also something called a selective reject. So I don't know whether to cover it at this point, but we'll have a primitive version of this from a data link point of view. Usually it is well and good to study that thing in the transport layer. Let's see. We do have time constraints dealing with each and everything in detail. I request you to go through the book, read a book. If you need any help, you can ask. At the end, if you keep it for the end, it will be a overload. You will find it very boring. You can make use of the slides to refresh your study of the subject. Very soon there might be a first internal exam. I am also preparing for that because the portions are to be covered. So error control, up till error control has to be covered, up to and including error control till the first internal. Very soon it should be happening. So we'll wind up for today.